so hollow with like their. It's so visible, obvious, but I don't know.
Hey man, how are you doing?
It was doing pretty good. Sorry if you missed.
It's okay.
I was trying to get a flight booked, but um, I took a practice test yesterday. I skipped the cars because Altius cars kind of useless. But what do you want? Where should we start?
Oh, like any questions you have on that practice test that you took?
Yeah, I haven't reviewed it yet, but I can share my screen.
Well,
we can just
before you look at the answers, I wonder if you can. Is it possible to show me like the questions that you had trouble with before?
Yeah, I can just do. Me just share my screen and just like skim, or I can kind of skim through it. But so when I took it, I feel like Altius Psych Soc is kind of hard. Like it's kind of different than AMC. Like I've gotten a 125 on like every single one of them. But like my last AMC, they're like a 29. So I think it's a little deflated maybe.
Yes,
but
it is.
So chem, physics, or whatever chemical process, I got a 124. And then bio, I got a 125. So like those two sections, just in general, I need to like bring up a lot. And I do think the biggest thing with the chem phys section, I have a hard time with some of the physics questions, the more conceptual ones.
Yeah.
Just because when I took physics, it was plug and chug, so I didn't really learn physics.
Yeah.
And then just the general math equations. And for biochem, I don't really know what I'm doing wrong. Like I think occasionally it's content related, but I think just sometimes the research passages, like I think I'm just missing things or making mistakes. So.
All right, let's go right into it. You can share your screen.
It's wrong one. It's the last one.
All right. Oh, okay.
You stop and go back. Or...
You could go to whichever one you want.
Okay. Yeah. I was good with that one.
Oh wait, this one?
Yeah, let me see. Did I get this one? Yeah, I got this one wrong. Yeah, I was like really confused. Like this orgo passage was just like throwing me off. Like I know what deamination is, and then the question is the bond is most likely to form between the amino group of the amino acid. I thought deamination's like when you like basically just remove the amino group, like you deprotonate it. And I was confused location wise where this was. Like it said the bond is most likely to form between the amino group.
Okay. So first I'm just gonna look at PLP and then look for it in the passage, and it seems like it's pyridoxal 5-phosphate.
Yeah.
Which is basically, it's the vitamin B6 that's phosphorylated. So you have a picture of PLP that's Roman numeral 2. Do you see it?
Yep.
Okay. So
yeah, I found.
Yep. So the amino acid that gets deaminated, it binds to PLP, Roman numeral 2.
Okay. I guess so. Like when I was going through it, I was confused. Like I knew A and B were wrong. And I was confused whether it was the carbon double bond nitrogen or the hydroxyl. Like I guess first of all, I read in the passage reaction 1 produces an imine. And then, but I looked here right away, and I knew to get here. I was just confused. Like, I guess I was looking at the O double bond H here, and then I saw the.
What group is that called, by the way?
Oh, it's an aldehyde, but I didn't see that.
Okay, yeah.
I was getting thrown off with the carbon double bond nitrogen imine linkage because I didn't understand how that was being deaminated. Because like I didn't see anything changing.
Show me where the imine is.
Is that it?
You know what? I think that is that, but a very basic version of it is right there in reaction 1. It's basically a double bond attached to a nitrogen. In reaction 1 above that. So it's basically
I looked there too.
carbonyl like a carbonyl group, but replace that carbon with nitrogen.
See, that's why I was confused because
Mm-hmm.
I'm not trying to like overthink this, but I saw the N and the R group, and I was confused, and I somehow was thinking, I don't know, that was this. Like I was torn between like I didn't know if they were referring to this or they were referring to this. I guess because I guess I was looking for a change, and like I did not pick that up.
Yeah, so okay, I would look at it like this. So they're saying, so it just starts off by saying like imines, imines, whatever. Like they have a formula of basically a double bond to a nitrogen, right?
Yeah.
So you can get that by taking an aldehyde or a ketone, right? And you react it with a primary amine, and that's shown in reaction 1, and then you get the amine. That's just, so basically what happens is that double bond to the oxygen, you replace that oxygen with a nitrogen. Sorry, I said carbon before, but you replace the oxygen with a nitrogen.
Yeah.
And, and then they say that B6 is a precursor to PLP, which is a coenzyme, blah, blah, blah. It attaches to the enzyme protein chain by an imine linkage. And, okay, and it catalyzes the deamination of the amino acid, right? And then it says PLP accepts the amino functional group of the original amino acid to form the PMP, which is Roman numeral 3. So that's that first stage, right? So basically, Roman numeral 2, that structure, PLP, right?
Yeah.
So that is going to accept like the amine group of a, let's say any like given amino acid to make the thing that's on Roman numeral 3. So from 2 to
they're
3,
saying
what changes?
the NH. So they're saying the NH bond would take the amino acid. Is that what they're saying?
The NH bond, the amino group of the amino acid, that is going to interact with something that's on PLP, like Roman numeral 2.
All right, yeah, because so this is exactly like the issue I have, like with a lot of questions that I miss. Like I'm like 50-50 there, and I picked the wrong answer. Like I was a little bit tempted to pick the imine or whatever it is. I just wasn't exactly sure what that was, and I like see that it was in the passage, but I don't know. I just felt like it was wrong to me, just because I guess I was looking for the change in the structure, because I was like looking at, I don't know. Like I kind of see it now, but I was like looking for something to happen with the NH group on that double bond, because I know what I know what deamination is. So like I don't know.
Yeah. So look at the structure of Roman numeral 2, and like then look at, I guess, Roman numeral 3, or rather, since sorry, my bad. Roman numeral 1 to Roman numeral 2 to Roman numeral 3 is going in the direction of amination, I think. Let me see.
No, I think you're right. I was not thinking.
So we're going backwards. Deamination begins with binding of the amino acid to a PLP inside. Okay. So, and then they're saying that Roman numeral 1 is the precursor. So it forms PLP, which then forms the third Roman numeral 3. Okay.
So I guess reaction to the aldehyde, somehow the oxygen is leaving, and somehow later on it's being aminated. That's probably not the right word. Like I think I just had it backwards, because I've seen deamination questions. I know what it is, and I guess I was like reverse thinking it. But also I should have known that wasn't a hydroxyl group. That was a aldehyde, so that should have eliminated that answer.
Yeah. But
I kind of get in a frenzy too. Like when I'm trying to go through these tests, sometimes I kind of get in a frenzy and like crap. But yeah, all right.
It seems like what's happening here is from Roman numeral 1 to 2, you have a hydroxyl turn into an aldehyde group.
Yeah.
Right, and then from Roman numeral 2 to Roman numeral 3, you have an aldehyde group turn into an amine, right?
Yep.
So if you look at reaction 1, right, you have a like ketone, but they said that you can do it with an aldehyde or ketone, like in the first in like the second sentence, right?
Yeah.
So it's just that in the reaction 1, they use a ketone as an example, but that can be an aldehyde. But if you add that aldehyde, like in Roman numeral 2, to just an amine, right? And in this case, they're saying it's, here, I'm going to do what I did last time, which is take a screenshot, and then I'll draw it out here. Use whiteboard. All right, I'm going to share my screen, okay?
Okay.
All right, so check this out. Oh wait, what? I have to put in my password. Hold on. I always have to put in. I always change like my Microsoft password. It's impossible to remember. Okay, I think I got it. Okay, cool. So, all right. Let me get to it. All right, so, okay, so this over here is a ketone, but it can also just be an aldehyde, like that. Oh, it's not writing on top of it. Okay. So, yeah, so I drew the aldehyde. So, and then they add an amine to it, right? A primary amine. So
Yeah.
here we have, you know, an aldehyde. And then here we have a primary amine. And the question is talking about PLP, right, binding to the amino group of the amino acid, right? So basically you have, you know, an amino acid, which basically looks like this. With like an R group, right?
Mm-hmm. Yep.
So this is the amine group of an amino acid, right?
Yep.
So that is going to bind to something on PLP over here. So we have to basically figure out which, like, the amine group, like, what is it going to, like, really, like, attach to? Because we have the phosphate group here. This is the pyridine nitrogen over here. The CN, like, this is the amine linkage here, right?
Mm-hmm.
And this is the hydroxyl group over here. So that's what they're asking. They're asking which of these, which of these is it going to attach to? And I see like an example here of, so basically everything stays the same here except you have a hydroxyl group here, right? And everything stays the same here except you have an amine group here. And then, you know, this is just an aldehyde group. So like I would look at like basically like what changes. And also for, you know, any type of carbonyl bond, right? You know, like where the partial positive charges and stuff are, right?
Are you talking about like, excuse me, like an amino acid in general, like the
here, I'll use green. Like this is like a partial positive charge, partial negative charge.
Yep.
Right? So that means that like a nucleophile is going to attack that carbon, right? Did you check out? So in one of the things I shared with you, I go over like organic chemistry in like a really like short way. Do you see it? Like I have it on my screen now. You see it?
Yeah, I see it.
Yeah, like if I were to sum up organic chemistry, it would just be basically how electrophiles and nucleophiles react. Electrophiles are Lewis acids, which are electron pair acceptors.
Okay.
And, they're going to be positively charged because they're going to, electrons are going to go towards them. And nucleophiles are negatively charged. They're electron pair donators, so they're going to be going towards things that are, positive or partial positive.
Those are like usually like alcohols.
So in alcohol, right? So an OH group, what would it be something that donates its electrons or donates its electrons or accepts?
I'm trying to like visualize that. Hold on. So I mean, aren't there usually like free electrons to donate on alcohol? Yeah, on alcohol.
Mm-hmm. Yeah, basically it has an oxygen which is pretty electronegative, right?
Yeah.
So it's gonna basically have lots of electrons, so it's going to be functioning, as a nucleophile, as an electron pair donator. So that's like what an OH group would do. So it would look like, let me zoom out here. So basically, if you have something like this, and you have like an OH group or something, right? This is going to have, these lone pairs, and it's going to attack that. Sorry, this pen is acting up. It's going to attack this partial positive end of the carbonyl group, causing, this double bond, the electrons of this double bond to go towards the oxygen, and what it would then turn into would be this. So this guy attacks that, forming a bond. This double bond, the electrons go towards the oxygen, so you have a negatively charged oxygen here, single bond, and a new bond formed between the hydroxyl group and this, carbon over here. So you see how they're all connected here?
Yep.
Yeah, so that's what they're basically asking. So they're basically asking, so like here's like a regular, amino acid, right? With the R group, could be anything, right? And it makes a link with this guy over here, the PLP. And they're asking which bond is going to form between the amino group of the amino acid, this over here, and something on the PLP over here.
All right, so to circle back real quick, the aldehyde group, what was that bonding with? Was that bonding with PLP?
So the aldehyde group is already on the PLP?
So something else is binding to PLP with that amine? Imine.
So this amino acid over here is going to be binding to something on this PLP over here.
Okay.
So we have to see, and it's going to be binding specifically with this amine group over here. So what over here is going to attack that? What I showed you here is an example of the OH group being, attacking like a carbonyl group over here. But just because this has a carbonyl group doesn't mean that, because they're not asking about an OH group that attacks it. But I just use this as an example so you can see that it's the OH group of this that attacks that.
So for like that aldehyde group, because of the oxygen electronegativity and like I guess the free electrons that can interact, it acts as a Lewis base, so it can donate those electrons. So basically making it like decent nucleophile.
Exactly.
But the nitrogen has that positive charge, so that means it's an electrophile, so it's going to accept electrons from something that we don't know what it is. And
exactly.
It.
Yeah.
Okay. Yeah, I think I was trying to like look at it from just like memorizing my functional groups, but yeah. Okay.
Well, it seems like you have them memorized, which is good.
Yeah.
Just
I could have gotten it right, not being stupid with the hydroxyl thing because that wasn't a hydroxyl group, but yeah, so that makes sense. And then also,
this is also a good time to tell you that STY, the amino acids serine, threonine, and tyrosine.
Yep.
They all have hydroxyl groups. So when something gets phosphorylated, it does so using these amino acids like 99% of the time because they have hydroxyl groups.
Is that like the catalytic triad or is that something else? I can't remember from biochem. It might be a catalytic triad.
I'm not really sure, but I think I wrote maybe somewhere here about how those are just the amino acids to know that participate in anything getting phosphorylated.
Gotcha.
It's the gamma
phosphorolases. Yeah.
Oh, well, that's a little different. So like,
are they serine or proteases usually, right?
It's like a kinase. That's like how a kinase works. Here, let me see if I can find, because I drew it out once before. Oh, you know what like an amide is, right?
NH2.
Yeah, an amide.
Yeah.
It's basically like a carboxylic acid functional group, but you replace the OH with the
NH2.
Got it. Yeah.
Yep. Yeah, I know my amino acids, but I didn't even think about that as far as like the what you said about the OH. Like I knew they had an OH group on them, those three, but I didn't think about it in terms of like relating it to this.
Yeah, that's why like I always think it's like when people say you have to memorize all the amino acids, you can have them all memorized, but you still wouldn't be able to answer that question if you don't know what's important about the amino acids. Like STY, like those amino acids all have hydroxyl groups, and those are the ones that participate in phosphorylation. They basically take the gamma phosphate group from ATP, and they take it and hold on to it, and then they give it to whatever thing gets phosphorylated. So, the more information and content. Here we go. Do you see this right here?
Yep.
So
okay.
So this is like a question. During phosphorylation of stat 5b proteins, phosphate groups are exchanged for what atoms on tyrosine residues? So kinase basically works by helping an OH group on these amino acids nucleophilically attack the gamma phosphate group, which is the third one of an ATP, resulting in the amino acid residue acquiring a phosphate group. So here's an example. So I didn't write out, serine, threonine, or tyrosine. I just drew the, OH group. All right, you see that?
Mm-hmm. Yep.
Okay, and this is just some random base that's in solution because I want to be like usually like it's not really important to think of it that way. I just wanted to be like really like precise, but like here I didn't draw anything taking the H away, so you don't have to worry about that as much. But primarily it's the same kind of thing. The the oxygen essentially nucleophilically attacks something, right? So this oxygen nucleophilically attacks this phosphorus atom, causing this bond between this, phosphodiester bond to break. And then you have an oxygen attached to the phosphate. So now this amino acid is phosphorylated.
Okay.
So, yeah, remember that when it comes to, like add that to like whatever list of things to know about amino acids that you have.
Okay, cool.
Yeah.
Yeah, I mean, felt pretty good about most of those, but that was full time. Also, while I'm not trying to switch over to acid-base chemistry right away, but like while we were on it, we talked about nucleophile, electrophile, or
yep.
What was that screen you had up?
Oh yeah. Like a nucleophile being a Lewis base.
Or hold on, that last one you had up for me, the one with the where he talks about
This
the
one?
Yeah, that one. Sorry.
Yep.
Okay, yeah. So I have a hard time memorizing. So yeah, the Lewis acid, the electron pair acceptor versus the Lewis base electron pair donor.
Mm-hmm.
I feel like I have that down because they usually say it in that terms. But there's also the whole Bronsted, Lowry, and then there's the other one, and I get confused sometimes which one is which.
So yeah. So there's the Arrhenius definition.
One has to do with like the protons, the proton donor acceptor. Like it's like backwards or something. I always get that wrong, like confused.
Oh yeah. So okay, the Arrhenius definition is an acid would produce hydronium, a base will produce OH minus.
Yep.
Bronsted Lowry, it just involves proton acceptor, proton donor. However, so that means like as we go into these definitions, like how could I put it? All right, so a Bronsted Lowry acid will always be a Arrhenius acid, but not vice versa.
Okay.
So Lewis acid and base, those definitions are always true. Like it's not always true that an acid would make OH minus, right?
Yeah.
But it's always true that an acid will accept an electron pair. That's why, like, me talking about organic chem as being simply reactions between Lewis acids and bases, that's usually not how people would define organic chemistry, because we think of acids and bases, like, in terms of protons and stuff.
Yeah.
But I think it's best to think of them as Lewis acids and bases. Because, like, for instance, like, here I have, like, a list of, like, basicity. And, like, CH3 minus isn't OH minus, right? So it's not an Arrhenius, base. It's not, accepting protons or anything, either. So it's not really a Bronsted Lowry one. But it's a Lewis one. But yeah, since most acid base questions are involving like protons and stuff, it's probably best to just think of them as electrophiles and nucleophiles.
Yeah, I don't think. I mean, maybe I've seen it come up as a discrete. I don't think I've seen Arrhenius anywhere, but maybe as a discrete, they asked like which one was the Lewis acid or whatever.
Mm-hmm.
So Lewis acids are electron pair acceptors.
Mm-hmm.
I'm trying not to get this mixed up in terms of the protons, though. Like I know the more basic it is, you have more OH minus ions floating around or whatever. And I know the more acidic it is, you have more of the protons floating around.
Yeah.
So
like, yeah, think of it like if you're thinking of it as an acid that donates protons which are positively charged, and it gives away something that's positively charged, it's going to be likely to accept something that's negatively charged.
Okay,
like
gotcha.
In order for it to be neutral, right?
Okay, cool.
So, yeah. And then the rest of this I talk about nucleophilicity and how it's not the same exact thing as basicity. But this is mostly just, if you wanted to think of orgo in these terms.
Gotcha. Yeah. When I took Orgo 1 and 2, was thinking of it in terms of memorizing every single reagent you can. And just,
Yeah.
it was not like this.
In terms of that, I would look at what I wrote about here, this type of thing. Where is it? It's like where I drew like oxidation and like reduction and how it affects. Here we go. So this is what you should know. Like left to right involves oxidation, which is the same thing as catabolism, like the breaking down of products. So most like glycolysis, like Krebs cycle, all that stuff. Those are catabolic pathways, which are oxidative pathways. So make them like the same in your head. So a single bond, if it gets oxidized, it's going to make a double bond.
Okay.
And then if it gets oxidized again, it's going to make an alcohol. Now, if it's a tertiary alcohol, that's the end of the road for that guy because you can't oxidate any further. If it's a secondary alcohol, you can oxidize it to make a ketone, but you can't go any further than the ketone. If it's a primary alcohol, you can oxidize to make a aldehyde, and then you can oxidize again to make a carboxylic acid, and then the last oxidation would be carbon dioxide.
Wait, that would have been really helpful a long time ago when I was taking Orgo, because they don't teach it away.
Yeah. And then, and so like you would see this come up a lot in biochemical pathways, metabolic pathways with NAD+, NADP, FAD, H2O even. And then opposite direction would be reduction, and so that'll be done by like, NADH, NADPH, FADH2, and instead of water, oxygen.
Okay. Yep.
Yeah,
that makes sense.
I've seen questions like that where you'd like I saw a question that was like I think like quinoline or something, quinolone gets reduced into what, and quinolone.
I think it's all that. It was an AMC. Yeah, I think it's all that one. I think I got that right. But yeah.
So what type? So quinolone, just from its name, what functional group are we looking at? Forget the quin part, because that stays the same, right?
Isn't it alcohol?
The ONE, it ends in ONE, right?
Oh, yeah.
So if it ends in ONE, what functional group is that? Like, what's a functional group that also ends in ONE?
My brain's not working right now, but
think about it. So here we go. So is it a alkane? Is it an alkene? Is it a alcohol? Is it a aldehyde? Is it a ketone? Is it a carboxylic acid? Carbon dioxide? Which one of those ends in -one?
That was ketone, right?
Yep.
So I know the double bond O with R group on each side, right?
Yeah. So a ketone, if you oxidize a ketone, what would you get? You can use the thing that I have on the screen.
So you get a carboxylic acid?
Kind of a trick question, though. Try again.
Hydroxyl, I can't.
So okay, what's this over here?
Oh, it's an aldehyde.
Mm-hmm. What's that?
Ketone?
Yeah. So it was a kind of a trick question because you can't oxidize a ketone.
Oh, okay.
But the question that you're thinking of in the AMC one was like, what happens if you reduce it? If you reduce it, what happens?
Okay, so yeah, if you reduce it, do you get an aldehyde?
So from
I keep thinking of this in terms of like protons, like.
Oh yeah, no, just look at it like this. Like left to right is oxidation, right to left is reduction.
Okay, so you said it's being reduced, right?
Mm-hmm. So is it going to moving? Is it going?
So it's going left. So
Yeah.
it's going to the CH double bond CH.
This one, if it goes left, would go here, right?
Oh wait, yeah.
And
so
what are
secondary
these?
alcohol.
Yeah, it'll make an alcohol basically. So it'll make like quinol or something like that, or whatever it's called. Like basically, like in terms of the functional groups, know what happens to them when they get oxidized and when they get reduced. That way, you'd be able to solve like any of these.
Okay.
Because like that
So
question,
I have a note notes with like a bunch of functional groups. So I guess I could just kind of get them out and practice it like that.
Yeah, you don't need to know like crazy ones like nitrile or.
Probably just like what like maybe don't need to know like amides, alcohols, carboxylic.
Yeah, you need to know
like,
those.
Aldehydes.
Yeah. Yeah, those are the ones you need to know. I sent you my Anki deck, right?
Yeah, you did. I got it.
Yeah, I have I like go over some of them there. And I have like the ones on math also that, obviously I want you to do. But yeah, I go over that stuff also.
Okay, cool.
Yeah, here's also some stuff like, carboxylic, like this is how to make all the like carboxylic acid derivatives and amides and stuff. Oh, and then here's an oxidation pathway for alcohols and stuff. So yeah. All right.
Okay, cool.
You can share your screen again.
Oh, smart. Okay.
So let me just quickly ask you this. Roman numeral 2, right? If you want to go from Roman numeral 2 to Roman numeral 1, do you reduce or oxidize?
All right, so isn't like the double bond going to like send off the electrons? Like I'm just like saying arrows like off, so isn't it going to lose electrons? To go back to
if it reduces, like it'll
reduction's gaining electrons, right?
Yeah, you can also think of it as like the addition of hydrides. They usually don't talk about it that way, but that's another way of thinking
like
about it.
I guess I'm so used to looking at it from just the biology perspective of protons, like I just so like if I would say it's being reduced.
Yeah. Good.
But I think of it in terms of protons usually. I don't know why. I guess sometimes I have a hard time seeing the electrons, but
yeah. Like so yeah, there's something called a hydride. I'll talk to you about it like I guess next time something like this comes up because that's another way of looking at something that gets oxidized or reduced instead of just electrons. Like like when NAD plus turns when it oxidizes something, right? It turns into NADH plus H plus.
Okay.
That H in the NADH is a hydride. It's basically a hydrogen with 2 electrons, so a negatively charged hydrogen. They usually don't tell you that, and people usually think it's just like a proton, but that wouldn't make sense, right? Because if it's NAD plus and it goes and makes NADH, which is neutral, how could you add like another positive charge, right? It has to be something that balances out that positive charge.
Okay.
So, wait, do you want to do this one?
Maybe just got the right
alpha keto acid.
I got it.
So like
I got it right.
Yeah.
I knew that D and or not D, C and D. I knew those were wrong right away, but I'm trying to remember how I got it right. Let's see. Okay, well I knew alanine, so CH3, so I knew this was out.
Because that's like glycine, right? It starts off with glycine.
Yeah. alpha keto was transamination. I'm trying to remember where everything was at in the passage. I think I knew. I think the number of carbons in here was wrong, and then I think because of it said alpha, so I knew that was the alpha, right? Carbon. That's the alpha carbon, isn't it?
I think the alpha carbon is the one that's next to. Wait,
I thought you did
from the perspective of the carbonyl group?
The carb, yeah, that's what I was saying. I think this is alpha. I think
it's the relative to the carbonyl group, it's going to be the one the CH3 there. But they're asking for an alpha keto acid, so the alpha is going to be where the ketone thing is. So it's going to be relative to the CH3. Here. I'm going to send something. One sec. Alright, so I'm doing copy image address, so I'm going to just share it in the chat. So, yeah, open that link up so I can see it. I sent it in the chat.
Okay.
In the Zoom chat. Alright, so this is an alpha carbon, right? And relative to the carbonyl, right? And you see how the alpha position is the one that's not connected. It's not part of that carbonyl group.
Oh, okay.
All right, now I'm going to send you this. All right, try that next link. Yeah, that one. So now this is for alpha keto acids. So this is what you're thinking of now. And for an alpha so for an alpha keto acid, that is when it's going to be, because the alpha, so that first picture is the alpha carbon. So it's going to be a regular carbon, right? For this, since it's an alpha keto acid, the alpha corresponds to where the ketone group is. So that's why it's going to be...
Oh, yeah.
Yeah.
Okay.
And so, for instance, pyruvate, pyruvate, right, is a good example of an alpha keto acid. Okay, you could show me that. You could show me that question again.
Yeah, so I think I guess I was right. I was right on the right track because I knew the others weren't the right position. But I guess I when it said alpha keto, I was thinking of the position of the carbon, but yeah, it was on the ketone. That's why it was alpha, right? Alpha ketone. Versus this had some other functional group, it wouldn't have been. I don't know, it would have been something else.
Yeah. Basically, so you're looking at the thing that you chose. So the alpha keto acid version of alanine is pyruvate. So the one that you chose, that actually is the alpha keto version of alanine.
Okay.
Pyruvate, we talk about pyruvate all the time, right? And it's literally just alanine, but alpha keto acid version of it.
This was I had a very hard time with this question.
What's an ether?
Was what?
An ether?
I know it has to do with an oxygen, and I'm trying to remember the path. I can't remember if the passage showed it or not.
Okay, so.
It's where you have the oxygen between.
Yeah, between
any carbon and another R group or something.
Yeah, basically. I usually draw it oxygen and then two like bird wings almost.
Yeah.
So all right, good. What about ester?
Um,
I don't think that's in this one. I just wanted to ask you about
ester. I cannot remember, but like I know it has to do with oxygen too. It looks a little different.
Yeah, so it's gonna be just like a so. All right, wait. What was it? What was an amide?
And like a bond, like a NH2.
Mm-hmm. The NH2 will be where though?
What do you mean where?
Like, well, I mean, if it was just an NH2, it would just be an amine, right? But what about an amide? So okay, just think of carboxylic acid.
Oh yeah.
That OH turns into an amine, like an NH2, right? So it's a carbonyl group attached to an amine. That's an amide.
Okay.
Now, so it's based. So you know, you can imagine like a carboxylic acid group, like basically like a carbonyl group attached to an OH, right?
Yeah. So just basically like visualize it. It's like it's the same thing. Like you got your carboxylic acid, your amide, and like your with a H on the end, aldehyde.
Yeah. Now, if you replace that OH with an NH or whatever, it's an amide. If you replace it with an H, I guess it'll be an aldehyde. If you replace it with a carbon, it'll be a ketone. Now, if you replace it with an oxygen that's attached to some other stuff, that's an ester.
Okay, so like if you have that bond, you have the oxygen and it's attached to some other form of an R group, it's an ester.
Mm-hmm.
So real quick, circling back to the ethyl.
Yeah. Wait, ether?
Say it again, sorry.
Wait, you mean ether?
No, you told me I understand what the ether is, but we talked about the ethyl group.
Wait, ethyl or wait. Ethyl?
Wait, sorry. Okay, so like right here, well, it doesn't matter which one it is. So that's an ester, right?
Oh no! These are all ethers. I just wanted to ask you about esters.
Wait, the Okay, so in ethyl group. Wait, I'm getting myself confused now. This is an ether, so it's an oxygen to some R group and some sort of a chain.
Yeah. And
then you told me the east.
Oh, ester.
Ester.
Yeah.
That's just like That's just like if you saw a carboxylic acid group, except on the right side where there's oxygen, it would be connected to something else after that, like an R group.
Yeah, it would be essentially an ether in place.
Okay, I was making sure I understand that. I'm not like confused.
Okay, let's see. Carbon forms ethers similar to the silane ethers described in the passage, reacting which two species will produce a carbon ether. There's a lot of orgo on these Altius tests.
Yeah, it's really hard, some of these.
Let's see. So, okay. Carbon. So I see these, a silane one, another silane one, but in the two silane ones, there's also like carbon stuff added to like.
So like when I went through this like right away, I knew A and D were like I'm good about getting rid of the like outliers or the incorrect ones. Usually, like I knew it was an ethyl alcohol. I did not know how to deal with this and this. Like I don't know an ethyl tosylate. I know I've heard of ethyl tosylates before. I don't really ethylamine. Like I did not. I was trying to use this stuff in the middle here, the figure, and like it did not help.
Yeah. So okay, like so if you don't know what a tosylate is, you know what an ethylamine would look like, right?
I mean, yeah, I can kind of visualize that. It's just the ethyl with the NH2 at the end, right? On the
Yep. And you know, they're saying if you add ethyl alcohol. So like in figure 1, we see a lot of. I see that I see ethyl alcohol there. I see some non-ethyl alcohol stuff.
Oh, yeah, that basically already answered the question. So there was no amine in that drawing anywhere, so I shouldn't have gone with that.
Wait, no amine?
No, like it said an ethylamine, and there's no amine in anywhere in the drawing, right? Like,
well, yeah, I don't see anything there, but I mean, they're trying to just ask, how do you form? They're saying that carbon forms ethers similar to the silane ones in the passage. Which two species would react to make a carbon ether? So we're trying to create something that just has carbons on both sides, because everything that we have here, like two things have carbons on the right. Oh, okay. I think I kind of see something. So you see that thing on the left? It's like the R3Si,
yep.
then oxygen, and then an ethyl group, right?
Yeah.
And then they're adding 1-octanol and some enzyme to it, and it causes the ethyl group to leave. It turns into ethanol, right? Or ethyl alcohol. Like it leaves, and then that entire thing leaves, and you just have the R3Si with an OH, right?
Yeah.
So that's just showing you that that the ethyl alcohol can if you went backwards and you added, because what we see is from left to right is the ethyl group leaving with the production of ethyl alcohol, but if you go backwards we would add ethyl alcohol to it, and that ethyl alcohol would turn into the ethyl group, right?
I didn't at any point pay attention to where the ETOH part like that.
Oh yeah, that's definitely what I'm looking at, because
I just didn't see that. I kept looking at the 1-octanol transesterification enzyme, so where it made the octyl ether. I kept looking back. I didn't see that as a clue. I don't know, because I kept looking over the products because they kept talking about producing, so I kept looking at the products and trying to follow back.
Mm-hmm.
Yeah, because I was just trying to figure out how to get this right, how I would miss something like this again, because this was hard just because not that the AMC doesn't throw out random stuff at you, but this whole thing was kind of odd. I never learned anything about this octyl stuff in Orgo. And
I don't think you have to. All right, let's try this. So from the R3SiOH, right? Go to show me where that is with your cursor.
So here, what were we talking about? Say it again.
Yeah, that. So okay, when we add 1-octanol to it, right?
Yeah.
That's basically an alcohol with 8 carbons, right?
Yeah.
So then what happens to it? It gains that 8 carbon ether chain. You see that?
Okay.
The octyl silyl ether?
Yeah.
So
I wasn't even looking at that when I did it the first time.
Yeah, so all right, so this is basically what I looked at. So I looked at carbon ether, and then I always look at the pictures first, because
I just get overwhelmed and my God.
It's definitely overwhelming. That's why I'm not even looking at all this other.
Honestly, the Altius are usually worse than AMC, but this is helpful practice, obviously.
Yeah. I would look at, so they're talking about carbon ethers. The first thing I looked at was the picture, and I looked at which of these are carbon ethers. So that means an ether with carbons attached to it, right?
Yeah.
So show me where the ethers are and where the carbons attached to it are. For anything in figure 1.
Oh. Isn't it here?
So that's an ether, and then where are the carbons?
These are the carbons.
Bam, right? And then where's another one that has, right?
2 carbons, yeah.
And then you see how it relates to the type of alcohol that they're adding. Right?
Not exact. Well,
so the
position 1.
Mm-hmm.
So I mean that's what you mean, right? Like that's the position that the alcohol. That's why they.
Oh wait, what are you saying?
The
Oh, like
one octanol, the
yeah,
position.
when you add one octanol, right, to the R3SiOH, basically that the carbon chain of that alcohol creates the other end of that carbon ether. So that's how you get the 8 carbon chain on the octyl ether.
Okay.
And then the
So
other
like,
one is going backwards to make the ethyl chain of that carbon ether.
okay, like just
Mm-hmm.
for my sake, because this is the kind of stuff I get wrong a lot.
Yeah.
It's just like like I'm really concerned too with like obviously like the timing of all of it because just doing it like fast paced. Like I knew it was between B and C. I picked
What made you
ethylamine
think?
probably on a whim.
What made you think it was like? What made you um
I don't know.
be
I
able to
actually
do
had a
that?
gut instinct to go with B, and I didn't because I couldn't remember what an ethyl tosylate was, and then I don't really know why I picked the ethylamine
So
now.
so
Like
think about ethyl alcohol and tert butanol. How are they like different?
I don't remember exactly what terbutanol is. I just think it's the Churchill. It's like deals with the carbons, like the way they're
Mm-hmm.
positioned,
Yeah.
like a tertiary, like the tert group. Yeah.
Tertiary, right? And what is tertiary like? What's with that? Like, like tell me about tertiary stuff.
Um, I can't like exactly like I just think of the number of carbons and like how it's positioned like on some sort of like I don't know skeletal structure. Like
So remember when I was showing you like that oxidation thing, and about how tertiary alcohols can't be oxidized further?
yeah,
All right. Why do
is
you?
that because of sorry, go
Yeah.
ahead.
Well, yeah. What were you gonna say?
I was just saying is that because of the steric hindrance?
Yes. Good.
Okay.
Think of it like that. Now, let me ask you this to connect it to something we talked about yesterday. I mean, last time we saw each other. What type of what type of ion is the most stable? If you have the choices primary, secondary, tertiary.
Wasn't tertiary most stable? Because
Yes.
yeah,
So when you think of tertiary, think of those two things. It's the most stable form of an ion because it has so much space for that charge to be distributed. But also think of it as steric hindrance because it has so much space, it gets in the way of things. Make sense?
yeah,
So, yeah, so you were able to know that the ones with tert butanol wouldn't really work because if well,
They're-
first of all, like
yeah,
I guess if you don't know, like you're gonna just look at two choices that have tert, and tert means it's the most stable type of ion and it has the most steric hindrance, and then you have two things that have ethyl alcohol, which basically is primary, which basically means that it will be the least stable as an ion.
but more
And
reactive.
exactly. And then
Yeah,
also
I knew alcohols were reactive too. So
remember how things that are least stable by themselves but become more stable after a reaction are more reactive, right? Like
yeah,
an acid that has a more stable conjugate base is a stronger acid, right?
yeah.
So we put all those three things together so you can connect all those things.
I just feel like these questions sometimes are asking for a lot of info that like in a very like short period. You have like a minute to answer it.
Yeah, but if you can boil it down to just those types of things, then
Yeah.
you'll be able to answer it without.
So the only thing I
worrying
still
about
don't understand still is the whole ethyl tosylate and ethylamine. Like the only thing reason I see the ethylamine was a stupid choice is because there's nothing going on in the reaction with amine. So I guess that could have gotten me to B right away. Or am I looking at that wrong? Like there's nothing in there that suggests that there was any sort of.
Oh wait, you're saying like as ethyl tosylate
Or like
versus
why C is a
ethylamine?
bad answer because the ethylamine's not. There's nothing in there about that.
Let's see. Nothing in the in that chart says anything about that. Well, I mean, I don't want to use like what we learned in that previous question, but we did a previous question where the amine group of an amino acid attacks the hydroxyl group, the OH group of PLP, remember?
Yeah.
To produce a like an aldehyde or something like that. So that could be something that would make you not choose ethylamine, because that alcohol and amines they basically react to do that. But you want something to basically leave. If you want to produce an ether, right? You want the thing that was there before to leave. So you basically want the ethyl group from the ethyl alcohol to connect, and then you want something from the other thing to connect. So if it was an amine group, we're going to have, we don't really want an amine to be there if you want to make an ether.
Gotcha. And I don't think I knew, I didn't ever remember reagents and stuff that much, but I didn't really remember ethyl tosalate's function.
Mm-hmm.
Because it says in the answer solution that it would be a good leaving group, but
wait, what did it say?
Oh, I was just saying the answer is the ethyl tosylate, but I didn't know that was a good leaving group.
Oh yeah.
Yeah, that's just something content wise I didn't know.
Mm-hmm.
Yeah.
Yeah.
So this is just an example of something that I'm close
about it in there.
Say what?
The tosylate doesn't say anything in that. All right, that's pretty unfair, I guess.
Yeah.
I think the tosylate or something is something to do with. I thought that was the T.
I don't think there's anything in here. Yeah, I don't think there's anything. I think that was sort of a pseudo discrete hidden in the question, but I mean the only way I can see that I could have gotten to the answer was not thinking about the amine, just because it wasn't in the reaction anywhere, and I felt like if it wasn't in the reaction, it probably wasn't going to be.
Mm-hmm.
So yeah.
Okay.
But I mean, I know these questions are a little bit harder than AMC. I mean, they could feasibly ask something like that, but
yeah, I've never seen anything about them making it so you have to know what a tosylate group looks like.
Yeah, they're probably just trying to make this really hard. Which is fine. I learned something, but yeah.
And nothing down there either. Okay.
Yeah, I didn't see anything. This was a really tough passage. There was a lot of crap in here.
Mm-hmm.
And this, I didn't know how to do this at all. I know what a lipase is.
What's a lipase?
They help. They're an enzyme that help break down fats and stuff.
Mm-hmm.
I think of them in terms of digestion and
mm-hmm.
all that.
Good. What's a protease?
I think of proteases like serine proteases, which I think are part of the catalytic triad, and they
just think of the word, right? Lipid.
They help break down proteins.
Breaking down, yeah. What about nuclease?
Yeah, my biochem professor is obsessed with knowing all the intricate details, which.
Oh yeah, I think word etymology is makes you be able to figure out almost anything.
Sure.
What's a nuclease? What's a nuclease?
Nuclease.
Think of what else could you break down? We talked about fats. We talked about proteins. Something that may be sounding like
nuclear membrane. I don't know.
Nucleic acid.
The nucleus. I don't know.
What? So what other building blocks are there?
All right, so we've got amino acids, fats. We've got carbohydrates. We've got the fourth one, the Well, I can't say it. The
It starts with nuclei.
Oh, nucleotides.
Yes, nucleic acids.
Yeah. Oh,
Yeah.
little brain fart.
So yeah, try to think of things in that type of way. You'll be able to. That way you don't like have to necessarily remember what a lipase is or a protease is or blah 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 is. You can even answer like stuff like hydrolase and stuff like that.
Yeah.
But generally speaking, like ACE is going to be it's going to be a enzyme.
Yep.
So okay, this thing lipase also exhibits lipase activity. What? I mean, it is a lipase. Of course, it would do that.
It's lipase activity. Yeah, it was written early, amazingly. On the tag, so
the product formed by the action of this lipase on triacylglycerol substrate is most similar to which of the following? Triacylglycerol. Tell me about that.
yeah, so tag, so like triacylglyceride, so like I think of like cholesterol, and think about
so like a lipid,
like
right?
the free fatty acids. Yeah.
Yeah. So a lipid, like
Tag's
it
broken
has.
down. Yeah.
It has like the. It's the combination of like the glycerol, which has like the and the fatty acids. They combine to make the triacylglycerol, the lipid.
Yeah, and don't you break down? I think you break down tag into two fatty acids and like a monocyl glycerol or something like that. I know you break it down. You can break it down to get those. Things.
Yeah. So okay, let's see. They're saying product by the action of this lipase. To say this lipase, so they're being specific. So let's see. They're oh I see. So this is going to be we're going to look at table 1. Because
like it was really I hate these long ass tables and like crap. Like they did this on purpose just to make it hard, but
yeah. But you'll know where to look because they're basically saying that they're going to try adding like all this different crap to these different types of things, which are all choices, right? And they're trying to see like let me see that question again. Like the question stem. They're saying okay, so if you add that lipase to a triacylglycerol, what would it do? Okay, so let's look at that chart. So the where's that lipase? Okay, the rhizopus lipase. I see that
here
and there, right? Okay.
Yeah, that's only two I saw.
So if we compare it to the they do it for
is it the second? Isn't two? Hold on, was it? I can't remember if it was the second one or first. I think the second one's actually the tag. I'm trying to remember. Maybe it's not. I know there's another question you had to use the second one.
The choices involve things from both. So the choices involve things from both. Like the PD stuff is in the second table, and the TME stuff is in the first.
Yeah. So this is the first. Wait, no, actually, it could be both. That one's in the second one?
Yeah. So that's the purpose of it. So basically,
let's
just take a look at what happens when we use the rhizopus or is a lipase, right? So
yeah, and I knew right away the percent yield meant that you're getting more of it. I assume.
Yeah, which means so. Wait. If the percent yield of the thing,
up here.
Let's see. What are they doing? They're adding the thing to the thing up top. Okay. So the negative control should produce more. Where's like the regular control? So negative control is supposed to give you a result that will work in the opposite direction. And
oh snap! I wasn't even paying attention to that. That might be why I got it wrong.
Hold on. Let me see. So comparing the numbers. Okay, so they tell you what these are. So they tell you that TMESI, right, is trimethyl ethoxysilane. And then TMS SiOH is the same thing, but instead of like an ANE at the end, it's an OL. So that means there's going to be a OH group, an alcohol group attached to it.
So like and I know why I answered what I did. I think I was trying to compare I can't say rhizopus, whatever. Yeah. I was trying to compare those numbers to the control because they were closest to it. I think that's why I went with it because I didn't TMSI. Where was that? Yeah, that's why I went with that. I don't know. This was a hard question for me.
Yeah. All right. So let's say we didn't even have that. Let's pretend that we don't let's not look at the question for a sec and just look at the chart and see how to make sense of the chart, right?
Okay.
So just for the negative control in octanol, right? 1 octanol, aka something that's a primary alcohol. We basically have a crap ton of the first thing, TMESI. We have 5.3 of that, 3.4 of that, 0 of that, right? Then we have a negative control, but water in a type of alcohol that has more steric hindrance. We have basically a third of the TMESI, so that changes dramatically. We have over 10 times as much of the TMSI-OH. That changes dramatically. HMTSI is kind of like a third. That changes somewhat. The TMO, blah, 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 the last column doesn't change at all. Right?
Yeah.
So between these two rows, it seems like mostly they're working in opposite directions, right? Except for that last column where it's just 0. Right?
Yeah.
And then, so I would just look at those two rows. I would compare the first two rows because they're basically the same thing. Just one is in, 1 octanol. You see that for for the rhizopus lipase 2 rows, it's first done in 1 octanol and then 5% water and tert butanol, right? And then the bovine 1 octanol, 5% tert butanol.
Oh, yeah.
So that's how we're going to compare them. We can't really compare negative control 1 octanol to rhizopus whatever lipase 5% and tert butanol, but we can compare the two that are using the same lipase or trypsin or something like that. So for this, I would compare the two lipase ones and how where is there the most substantial difference between everything else. It's that last column because we have for the negative control 0 no matter what. For the lipase 0 if it's in tert butanol, and for the bovine thing 0 if it's in tert butanol as well. So it seems like it's always going to be 0 if we're using TMOOSI, unless it's the lipase in 1 octanol or the bovine thing in 1 octanol.
Oh. So I was supposed to look at it in terms of, I was looking here the whole time. I was trying to skim through it, but there was a lot of numbers. So I was supposed to see that basically the negative control remains 0 in the 1 octanol and the tert butanol 5%. And I should have noticed these were similar and noticed that the rhizopus or lipase negative control is 1.8 and then it went to 0 under this condition, under the TMUSI. Yeah, I guess I see that. That was just kind of a tough.
It is. Cause yeah, I kind of
I knew this was kind of a distractor answer, and then.
So we're not done yet. I want to look at that table 2 to make sure that this is this holds true for, it's not just this. So let's look at table 2 now.
Okay.
All right, table 2. Look, basically. PDSI, right? Third column, it's all 0.
Yeah.
So that's useless, right?
Yeah.
Go back.
So I was just gonna double check the TMSAOH.
Yeah.
I guess there was no clear trend there.
I could
5 to 6
tell
to
you
4.
like a trend, but you don't like. So like basically like 1 octanol, 5% tert butanol thing. It's like more than 10 times, right?
Yeah.
For the negative control. For the lipase, right? It's basically just addition of like 10, which is barely anything. And then for the trypsin, it's like addition of like 40. But in every single case, the pattern is that in tert butanol, you have a higher percent yield. Is that true? That's true, right?
Yeah.
Now,
Okay.
TME-SI, it's going to be opposite. In the neg control, it's smaller if it's in tert butanol, right? The lipase, smaller if it's in tert butanol. The trypsin, smaller if it's in tert butanol, right?
Yeah.
HDMI cable is smaller in tert butanol, right? For every case, except for bovine thing. Do you see that?
Yeah.
Like, so in every case, it seems to be like there's that type of pattern. Like, you don't have to worry too much about the specific numbers. Just note if it's first of all, like, know what to compare. You're going to compare like if it's in 1 octanol or tert butanol, and then just see if it's going to go up or down in either. And then the only thing that's different is in that last column. Because in that last column, basically 1 octanol causes a higher percent yield for everything besides the negative control. Now let's see if that's true for that last table. So the last table, I'll do it like column by column. First column, right? Negative control is worse in tert butanol, right?
Yeah.
What about the lipase? Better or worse in tert butanol?
It's better, right?
Better. The chicken egg white lysozyme, better or worse in tert butanol?
It's a lot better.
All right. What about the next column?
This one? Wait, where?
Oh, the PDSIOH.
Oh, yeah.
So for negative, better or worse in tert butanol?
It's better, right?
Mm-hmm. What about lipase?
Worse.
Chicken egg thing?
Worse.
All right. Next column, it's crap for everything, right?
Change. Yeah.
And then let's see the last thing, right? It doesn't matter for negative control. For the lipase, better in octanol. And for the lysozyme, better in octanol, right?
Okay.
So we basically can see that for the lipase in both situations, it essentially is better in octanol for the TMOOSI and for the PDMOOSI. So let's look at the choices. Oh, the PD whatever SI thing isn't even a choice, so it has to be the TMOOSI thing.
All right. Yeah, that was a pretty tough question, and timing wise, I feel like that was that's ridiculous. I think Altius are just ridiculous, but like it was good practice. I would say graphs are a major weakness. I do worse with tables, I noticed, than I do with like we'll see it later as we go. Maybe when we do bio, but I do worse, I think, with tables than I do with like the
like the
different types of like
that's why I hope it was helpful that we like ignored the question for a sec and just looked at the table and just looked how things changed, looked for patterns and stuff like that.
Yeah, for sure.
Okay, let's see.
A math one, and I'm trying to see if I wrote it down because I haven't reviewed this yet. I was trying to see if I wrote this down. I was trying to solve it.
You remember that E method?
Which one?
When I use the E, capital E.
Yeah.
So that 100 millimole, how can you write that?
I would have just written it as 0.1. Okay. Well, yeah. I'm saying by 10 to the -3, but 10 is
because let's say if it was nanomoles, right? it would be harder to write out the 0.00008 zeros in one, right?
Yeah.
Or 7 zeros in one. So I would just write straight up 100e negative 3, right? But
so
yeah,
I think I converted that right away to 0.1 by 10 or e to the 3 negative 3, right? I knew they were looking for grams.
So yeah, molecular weight is grams per mole, right? So we got the moles, right?
I was just trying to look back, see where I wrote this down. I might not be able to find it. Oh, sorry. Okay. So they're looking for grams of the T Moosey, and then I think I was trying to say sometimes I have a hard time just remembering where to start. I know we're trying to get to grams. They gave us the molecular weight, but they didn't give us how many grams it wasn't in the passage, I don't think. Like, they didn't give us the starting.
Well, they give you the starting amount of TMESI, and it reacts with an excess, basically unlimited amount of 1-octanol to produce how many grams of TMOOSI. So we have the molecular weight of TMOOSI. We don't have it for TMESI, but we don't really need it. We just need to know the stoichiometry of this, because it's basically going to be TMESI plus 1-octanol to produce as a product TMOOSI, but we need to see if it's a 1-to-1 ratio or not.
And also threw me out using the stat method. I was like, what the hell is that? Like, I talked about in the passage right here.
Yeah, that seems like it's they don't use an enzyme, I believe. They do, let's see. They do a transesterification without an enzyme. Yeah. Oh wait, but they're using bovine pancreatic trypsin. So we're going to be using that chart, I believe. So, yeah, so we're going to look at, so it starts off with TM, you can scroll a little bit up.
Oh, okay.
Yeah, so it says T, because it's hard to remember these TM craps. So let me just see it on the top, sorry, what we start off with. Scroll up all the way.
Yeah.
All right, so TMESI, right? So we're going to look at the column for TMESI and bovine pancreatic trypsin, okay? So that's going to be that first column, bottom to, whatever, right? Oh, and then it turns into the TMOOSI, right? So wait, first of all, the reaction conditions, does it make sense what's going on here? I just want to make sure, because what they're doing is they're using the reaction conditions, those are the reactants, and each of these things in the columns that say percent yield, those are the products.
Yeah.
Does that make sense?
I don't know. I didn't like this.
Yeah, so basically, so they're saying, they basically are saying that they're adding, so yes, so the reaction conditions, and we're going to be looking at, okay, let's see. So
wait, I think I know what I did now. Yeah, so when I sorry, I'm thinking. Yeah, so I started with this, and I was confused how to go from, so I wrote the 0.1 millimoles of TMSE, and that was for every 1 mole of the TMSE, you get 202 grams of the TMUSE, right?
That's if it's a perfect
1-to-1 ratio,
which I think.
And I guess I just guessed that because I couldn't find where that was at. Oh wait, no, I know what I did now. Yeah, I did use the graph, And I was trying to figure out based off the percent yield how to do this problem was kind of a lot, but yeah.
Mm-hmm. Yeah, so I would just focus on where it says bovine, the last two rows, right?
Where was that at?
Table 1?
Was it table 1? Okay.
Yeah, the last two rows. That's
these two. Okay, yeah. Sorry, it's hard for me to like talk when I'm in like
it's okay.
At the same time. Yeah. So yeah, I was here, and then we were comparing Team Messi to
to produce the Team Musi.
Yeah. So I didn't know what to do from here.
Okay, so like basically like they're basically saying like to make yeah.
Sorry, I'm talking. Oh yeah, I think I know what I did now because I'm just like remembering. I saw this and I was like 7 to 35%.
Yeah.
I was like thinking 1 to 5.
So all right, check this out. So above table 1, it tells you what like table 1 is based on, right? And they're saying that all these reactions starting material was TMESI. Do you see that?
Yeah.
Oh, like show me with your cursor where it says that.
Here?
Yes. So that means that that's what they're using as starting material. So everything in the column, those are the products.
Yep.
And the question is asking if we had, 100 millimoles of this starting product with the bovine pancreatic trypsin, right? How much T musi would be made, right?
Yep.
And so basically, it's going to be the percent yield of T musi is 34.9. So 34.9% of that's how much is going to be made. That much, like 35 roughly percent of the 100 millimolar is going to be 100. So first of all, it'll be that of the T musi. So basically, you're going to have the molecular weight of T musi and 35% of that.
Okay, let me try to get this straight here. So we're saying the T musi, which was 202 grams per mole, whatever the percent yield we produced, we got 35%. That would be the actual yield, right? This is the theoretical yield per mole?
Yeah.
So
that's the molecular weight, right? So yeah, basically, yeah.
Yeah, okay. So I would have taken this number, the 202. I'm trying to see how they did it. I didn't review this yet. This is the kind of, I get this kind of stuff wrong a lot. Some of them I do get right, but this one, the ones that require the graph and the steps, sometimes I get really lost. I get the ones I have the hardest time with is stoichiometry problems. I hated it when I took chem, just didn't care. And then anything involving concentrations, like ion concentrations, and I'm usually pretty good at finding grams and mole stuff. Stoichiometry, but this kind of one, these type of ones I have issues. Sometimes I have time figuring out where am I starting, where am I ending. But yeah, these are the kind of questions I get wrong a lot.
Here, let me share my screen for a sec.
That's good.
All right, so based on that, where it says the starting material for everything was that, so I'm going to draw out the reaction. So it's this plus 1 octanol, right, through the bovine whatever trypsin thing. That's like the catalyst, the enzyme. Produces T musi, right? Because it says the starting material for everything in table 1 was TMESI, right? So that's starting material there. And the question is saying with excess 1 octanol, so that's how we know in the table to not use the tert butanol one.
Okay.
And then in the table, we look at this last column, right? For the row that says the bovine trypsin. And then it basically produces like 35% of it. So we have 100 E negative 3 moles of Temesi, I'll just call it. And like, let's say X is the amount of Timusi we make, but it'll be 35% of that. So like something like that.
Okay.
All right.
Oh.
Mm-hmm.
I like that visual. That helps.
Mm-hmm. Yes. And okay. So basically, and then 1 mole of this is 202 grams. So we're going to use this amount of moles with the grams per mole of this and take 35% of that, and then that's how we'll find the total number of grams. So basically, like, this is excess. All of this is going to be converted into this, right?
Yeah.
Okay, so that means that let's see. Well, it'll be like this, like 35% of this, because that's going to be that. So it'll be basically here. So that X we pretty much know is going to be just that starting amount of this, because all of it gets converted.
Oh, okay.
Well, when I say all of it gets converted, I mean like none of this is left. So basically,
all of what we started with gets converted over.
Yeah, so 35% of this is how much of this is made.
Okay.
So I basically just, multiplied this by this to get that. So that's how many moles we're going to have of this, Timusi. What do you think?
About which part?
Does this make sense over here?
Yeah, can I see it one more time? Because I'm slow with math. So I know what you did. I got the 100 E negative 3. I'm so used to like doing stuff the other way.
Oh yeah.
All right, 100 E minus. No, it's fine. It's 100 E minus 3, and you're saying to multiply that by 0.35.
Yeah, maybe it'll be easier if I just.
I'm not. I'm really bad about like. I have to like multiply stuff. I have to like multiply it out like old school because like.
All right. How about this? So let's leave it at 100 millimoles. Because then we just have 100 to deal with and not the exponent stuff.
Okay.
So like 35% of 100 is just 35, right?
Okay.
So 35 percent of 100 millimolar is 35 millimolar, right? So
Oh, yeah, that's easier. I see that. Yeah,
Mhm.
so 0.35 by 10 to the negative. All right, that's easy. Yeah.
So that's how much of the tea musi you make.
Okay.
So that's in moles. I mean, in millimoles. This is what it is in moles. And since molecular weight is in grams per mole, what do you think we're going to do?
Can you just multiply it? I mean, on the bottom, you'll say 1 mole per 200 grams.
So the 202 grams per mole.
Yeah.
Where is it going to be here? Is it going to be like what? Like where is the 202 grams going to be? Where is the mole going to be?
It's the 202 grams is on top and the 1 mole is on the bottom.
Good. So I'm just going to do 2E2 grams and 1 mole. You said that, right? Moles on the bottom, right?
Yep.
So they cancel. So then I just have 35 times 2. What's that?
70.
And then what do we do with the exponents?
You have to move it. Well, so hold on, let's.
Mm-hmm.
Yeah, so. Sorry, hold on.
Mm-hmm.
So 2E2, so 2. And then, so it's to the 1. So, since it's. So you move it over 1.
So if you're
make it
multiplying numbers with exponents, you add the exponents.
Yep. So -3 and 2 is just 1. So you move it over to the left 1 time to make it like, say it like, so you don't have any more scientific notation.
Just you could leave it with the scientific notation. Like I would just do -3 plus 2 is just 2 minus 3, right?
Yeah.
2 minus 3 is -1, so it should be that. Right?
Oh, gotcha. Okay.
And that means that it's just 70, and we move it over to the left once. So 7, right?
Yep.
Yeah. So
okay.
Yeah. So the hard part here was again knowing what to use in the chart in the table, and knowing that from here that the starting material for all of the reactions in table 1 was this Temesi.
Yeah, it wasn't too bad. I just had a hard time setting. It took me like a minute just to figure out to go to that table and then figure. I don't think I figured out to multiply. I think I was trying to figure out like a mole ratio versus just like multiplying it by that percentage. Because I see that outside I used it all up or whatever. But
yeah, it is. You are right in that it is a mole ratio. The mole ratio is just 0.35.
Yeah, and they didn't give us like a reaction to look at, because normally I would just like look at a reaction.
Yeah, that's why at first I was trying to look for like clues, like stoichiometric clues. But then I realized that the table with its yield basically tells us all we need. Because it gives you experimental results. And if you have experimental results, you don't need the theoretical.
Okay. Yeah. All right. Yeah, that was kind of, I mean, it wasn't that hard, the math. It's just sometimes with them, it's like finding what
it's the chart.
And it sucks. And it's like,
yeah.
I'm almost at a point where I almost just want to flag math questions and come back to them at the end, because I feel like I'm just going to sit there for 3 minutes to solve it.
Yeah.
It's like my issue.
By the time we're done working together, you're going to be doing the math problems first. And
I wish they had somewhere
really
I could
fast.
just like go to do like MCAT math problems. Like,
yeah.
Not that when I took it last time, I only had a few math problems honestly came up, but
yeah. No, I
feel like they're freebies. Like if you know what to do, I feel like they're it's something you can solve and get points for. You know. Like,
yeah, that's I'll make like a bunch of like math questions for you.
Okay, cool.
Because it's
and also
just like practice.
Yeah, and also I changed my MCAT date to August 7th, so I've got another like 5 weeks.
Got it.
We'll see. Like I can always change it again, but I ideally like to get it done so I can get it back before it gets so late. But I'll go and share my screen. Can we keep working until like 10? Or
Yeah.
okay. And normally I would have like reviewed this already, but I took it yesterday.
Yeah.
Also, with UKeep, I feel like Altius is helping me a lot because they're really hard. I'm learning a lot of things. I'm on 5 now. I'll try to get another 2 or 3 done before I start. Like I might start AMC because I still have AMC 2, 3, and 4. I haven't done the sample in a long time. But but would you keep doing the Altius? Like
I feel like try to do it like without it being timed.
I did that for this one. I still got mad.
Good. All right.
I did this one on time. Yeah. I just got mad and walked away after that and we came back. But, yeah.
All right, let's see. This one, it says it uses 5% aqueous solution with either octyl alcohol or tert butyl. These solvents are effective because of their ability to serve all of the following except, enzyme miscible solvents. All right, so
I knew, I knew what that was just from learning about like the micelles and like chylomicrons and all that stuff and like fatty acid breakdown. So I knew that was true.
So like the miss part with the S in front of it, that just means that it you can mix it. So if it's enzyme miscible, it means that an enzyme can be mixed in it.
Okay, I was thinking of micelles though. Like
that's like actually what happens when it's not miscible. Like like when fats are in water, right? They're not able to mix because it's like a non-polar.
That's why they need micelles, right? It's
exactly.
To break it. So okay.
Yeah. So they're.
I just thought of solvents and not being miscible. I don't know.
Yeah. So basically we're looking for so if you look at like the charts, right? They're basically saying like when you basically 5% water tert butanol, they use the lipase, right? They're able to use
that's the key word, I think. Yeah, that was the key word that made me know that was true.
Yeah, so that means the lipase, the trypsin, they're both, enzymes, and the 5% water tert butanol thing, that can work, right? So enzyme miscible solvents, that works, right?
Yeah.
And then they said enzyme substrates. So enzyme substrate is a thing that the enzyme works on to create the product, right? So for table 1, what's the enzyme substrate?
Is it the trypsin?
What's that? Well, that's the enzyme.
Oh, wait, never mind. Trypsin,
So think about
what's acting on the enzyme
to produce the product.
Yeah, I'm not really sure. Like, so I know what a substrate is, especially like in terms of biochemistry, like when you talk about like allosteric reactions or allosteric enzymes and all that stuff. And I know like I visualize it, but like I'm not sure which one it is. Like I know it's not the trypsin's the enzyme.
Yeah, think of it in terms of that reaction that I wrote out. Like I know you don't have access to it yet, but if there's a reactant and then there's an arrow with an enzyme and then it produces a product, right? The enzyme helps that reactant turn into the product, right?
Yeah.
So the substrate is going to be one of those. It'll be because the substrate turns into a product, right?
Okay.
Right? Like a substrate, like the enzyme, like whatever, does something to a substrate to turn it into a product, right?
Okay.
So it's like the substrate's like a reactant, right?
Yeah, so the enzyme helps the reaction. feed forward, and like depending on the type of reactions, different substrates help that as well, I guess. Like
yeah,
like allosterically binds somewhere other than the active site, or
yeah. Like without thinking about allosteric, which is like a particular type where the enzyme kind of changes shape as it binds. Generally speaking, just think of an enzyme as it takes a substrate and it helps it turn into a product. So it takes a reactant and turns it into a product.
So I should have not eliminated that because one, the enzymes were always retained in the products anyway, and two, the substrates used to help form products. So I shouldn't have picked that. Okay.
Yeah, but in this table 1, which one is the substrate?
Yeah, I have no idea. I don't know what I know what the enzymes are.
What's the thing? The starting material?
I guess these are the substrate.
So remember when we found where it said what the starting material was for table 1?
No.
Try a little lower, a little higher.
Oh, sorry.
Like, above where it says table 1, I think it'll show you there.
Okay, the TMSE?
Yeah. So for everything in table 1, the starting material is the Temesi.
I guess I was thinking of that as a reagent, like our chemical.
Oh yeah. So like all these terms, like they're interchangeable. Like substrate is interchangeable with reactant, and reagent like is something that you just like add to it, which can be a reactant. It can be an enzyme. It's a much more general term.
Oh, I didn't know that. Okay.
But like enzyme turns a substrate into a product. So,
yeah.
And if the starting material for everything was Temesi, right? That means that, and everything starts off with that, right? That means that the enzyme substrate, which is Temesi, it can be in that like solution.
Okay.
Just like the enzyme can be in that solution, right?
Yeah.
And then let's see. The third choice is saying silyl ether soluble solutions. Solvents. And yeah, all of these things are that. Like trimethylsilinol, hexamethyl disiloxane, all these TM stuff, like they all have the silanes in it. So
that's why I need to pick that
C
one.
Is there.
I don't.
Yeah. But
I didn't understand. Yeah. I think I went with this one just because I didn't understand catalytic bases, what that had to do with the.
Yeah. So like for instance, like general. Tell me what the general like definition of a catalyst is.
Catalysts. They help speed up reactions.
How do they do that?
By lowering the activation energy.
Exactly. So like some examples of a catalyst could be an enzyme. Sometimes it can be an acid. Sometimes it can be a base.
So I see this is like where it's like I knew what this was and just told you what that definition was, and then I didn't pick the answer.
Try to think like as interdisciplinary as possible. Just because it's like a organic chem or biochem type of passage, like don't divorce what you know about like gen chem catalysts. Think of them like try to bring them all together. Like what you just gave me now, like basically was like an answer for a catalyst, and then catalytic bases is just if the catalyst is a base as opposed to an enzyme or an acid, right? Yeah. So we don't see anything. So we just have basically alcohol. We have a lipase. Different enzymes and stuff like that. But we don't have anything that involved like a base.
Yeah. Okay. Yeah, it just sucks. Like, I feel like I know a lot of the content, and I like
Mhm.
some things I know really in depth, and I get questions wrong because I feel like it's all tying back to the passage analysis and just thinking through it,
Yeah.
and not giving them more than they need, like to get to the answer. Like
Yeah.
even when I said all that, I knew a
Mhm.
lot, and then I didn't.
Yeah.
I
You
didn't,
can.
I didn't think about that at the time. I was like, oh crap, what does that mean in terms of this?
Yeah. All the content like won't really help you if you can't like connect it to when it's like, when you need it. But that is, that's why it's good that you're learning like to connect things.
And like this one I got wrong, and I'm kind of frustrated. And I'll see that like what is possible reason for the increased yield produced by the chicken, egg, white lysozyme. I don't even think you need to look at the passage to answer this.
Yeah, just like what are things that make an enzyme more effective, right?
Well, and I told you what that was. I thought the reactants are wait. It says reactants are correctly oriented, but I've never seen it explained that way before.
All right.
I was thinking it was stabilized by the.
So like a couple of things can make a reaction happen better, like increased temperature, which means that like let's say like this is an enzyme, this is the substrate, and they need to. This is all right. This is an enzyme. This is the active site, and this is like the substrate, right?
Yeah.
And it has to be in the active site to work, right?
Yeah.
So a couple of things can make that happen. If you increase the temperature, it'll make everything move faster. So it's going to like hit it more times. So like it can hit it this way, this way, this way. It's going to keep doing it until it hits the active site. So temperature means more attempts. So that can increase, the yield and stuff like that.
For sure.
Because you need, and if you have more of it, being like hitting more of the substrate, hitting the enzyme at the correct orientation, because it needs to be at the right orientation, that's also going to increase the yield.
So right away when I saw this question, I went with this. I knew right away I was like the product is stabilized by the enzyme's active site. I knew it had nothing to do with the product. That's just not true. And then the solvent is exposed to the enzyme's active site. I knew that wasn't true. The reactant is stabilized by the enzyme's active site. I knew that the reactant, you have a reactant, and in order for it to like overcome the hill or whatnot, you want to lower the activation energy, stabilize the transition state so we can get to product easily. Like you'll get product, but you're gonna get product way faster by doing that. I thought that's what this was saying. And I thought the orientation, I've never heard that in terms of seeing a biochem question where it was talking about orientation of the enzyme's active site, but
yeah. So here, check this out.
That's so commonly tested. Like I feel like they did this to make it a little tricky, but yeah.
So like usually like in high school they taught us like the lock and key kind of mechanism for enzymes, but that's like actually wrong. It's really like inducible, which means that like we were taught in high school like this is like the lock and then this is like the key and it has to fit in exactly like that. But what it really is like some weird shape like this, some weird shape like this, and as they get closer together, it changes shape to be just perfect.
Yeah, so conformational change.
Yeah, and if you didn't know that, if it was stabilized, if the product was stabilized by the enzyme's active state, it's not going to want to turn into anything else.
Remember, I didn't think of it in terms
if something's
of that.
Stable, it's not going to react. So if the product was stabilized, it's not going to want to turn into like the substrate or reactant. If the reactant's stabilized, it's not going to want to turn into like the product, right?
Oh, but wait. So we weren't. See, this was me just being familiar with vocab, but like, no, the reactant's not being stabilized. It's the transition state that's being stabilized by the enzyme, right?
Yeah, it's the induced fit. I'm going to send you like a picture of this.
Oh yeah, no, yeah, I remember. I know what that is.
Okay, cool.
Yeah. Yeah, that's just. I know this topic really well. It just sucks to get stuff wrong. Like I see that now, but like.
Yeah.
I guess because I've never seen it in terms of talking about it from a reactant perspective. Like, okay, I understand that now, and I know this concept really well, and I got it wrong. So, like that sucks, but This is like what I do on the test. Like I'm between two answers, and if I wouldn't pick the wrong answer all the time, I'd have a really good score. It's just,
yeah.
I feel like every time I take a test, this is like what happens.
Yeah. The orientation.
And it's not to do with content. Like.
Yeah, check out like the link I just sent you now.
All right. So the top one is the bottom. That might be this one.
Yeah, it's the latest one.
Yeah, so the enzyme, for the induced fit, the enzyme changes its active site. It undergoes a conformational change to fit in the substrate.
Yeah, so you see
the enzyme itself, it's not exactly made for the substrate. It just like accommodates itself.
Exactly. The old lock and key way, that would support, the it being stable, the enzyme being stable to the substrate or being stable to whatever the product. But it's the induced fit, which means that it's only stable when it's in that orientation, that transition state.
Oh. Wow. Yeah, like I knew this pretty well. I didn't think of it in terms of that question like that, though. Like that makes sense now. Yeah, wow. Okay. Yeah, all right.
Yep.
Learn something new. Or learn something in a different approach than like I thought about. Yeah, I knew that. That was just like that spin.
Oh yeah, so that was just remember like frequency
is
proportional
up, down.
to energy?
Yeah. Oh yeah, I don't know H&R stuff that well, but I think I knew right away it was the carboxylic group. I think just because it said high electronegativity and then
Yep, and you have, the high, so oxygen has high electronegativity, and you choose the one that has the most oxygens.
Yeah, I just knew that. I don't know a lot about that crap, like, in Orgo, I forgot a lot. I just knew this because I was familiar with, like, Twitter ions, and, like, I knew that. I just knew about, like, I just knew, like, where to take off. How do I say this? I know from like low to high pH what's happening in terms of like the protonation, deprotonation. So that's why I got that one. That was pretty good there. H&R signals. I saw a question I thought I learned from the last one. I knew it was 4 or 3. So metabolite A. Yeah, I thought that when you are naming, like knowing the amount of NMR signals, I thought that if there was 2 of them that were like the same type of, like the same, like for instance, I counted it, this methyl group is basically the same as this methyl group. So I thought it was just only 1, 2, it would produce 3 unique signals. And they're saying 4. Because I thought if they were the same, like.
Oh, it should produce 1.
Because here it says it produced 4, and I went with 3.
Okay, let's see. You have, so we're just looking at hydrogen. So there's 2 hydrogen, all right, there's 1 hydrogen. Oh, unique one. So there's 1 hydrogen on the OH, right?
Yep, so I knew that one.
And then that carbon next to it has 2 hydrogens, so they're not unique.
Oh, I wasn't counting that one. I was looking at it in terms of there were 3 methyl groups, and as far as position, I was thinking it was the same. I was thinking like this is 1, these 2 are the same, so that's 2, and this is 3. Wait, maybe that was right, but then I wasn't counting the carbons. Well, this would be CH2, right? And CH2. All right, I'll let you talk. Sorry, I was just like.
No. Keep going.
I was what you're saying. So, I think I said 1, 2. This is the same 3, and I think that's why I went with 3. But I wasn't accounting for the carbon. But those aren't unique because they're both CH2. So I just missed one of them. Is that why it was 4?
Yeah. So like if there's 2 identical ones, you just count it as 1.
Okay. Yeah.
So you basically have from the 2 CH2s over there, you count them as 1. From the 3, wait, one of those isn't even connected. Sorry.
Oh yeah, it's
So
not.
there's just two CH3s there, so you count that as one as well. I think that may have been what made you think
Oh
four.
yeah, I should have ignored
Because
that. So it
because
was not bonded.
yeah, that's
So it's
that's super
one.
tricky.
So this is one here. These two
Yeah,
are just one
yeah.
unique, and then 2, 3, 4 because it's closer to the oxygen, so it's different than this one.
Oh no, they're the same. That's why you treat them the same. The CH2, the two CH2s, you treat them as one.
Okay, wait, but why is it 4 then?
Wait, what's up?
But why is it 4 then if it's just one? These both are counting as one unique. That's 2 unique, and then there's a CH2 here and a CH2 here.
Let's see. Wait, trimethylated ammonium ion. Okay, so actually, never mind about what I said about the bond, because they say that it's trimethylated, so we count all 3 methyl groups.
Okay, I did the first time, but
Yeah. All right, so never mind what I said.
that's okay.
They're saying
So
trimethylated.
yeah.
Okay. So basically, let's see. 1, 2, 3. Oh, okay. Actually, you were right about the two CH2 groups. They are different because of what they're connected to.
Okay.
Okay.
That was just a whim. That was like a wild guess. I thought I learned that somewhere.
I don't know why they don't. I don't know why they're. Why it's like.
I just didn't understand why this 4 because I knew this that was unique. That was one unique. 1, 2, 3. So I don't understand why it's not 5 then. 5.
Yeah, I'm looking up choline right now. They messed up.
You think this one's wrong?
Yeah, here. No, like they messed up in the image. Here.
Oh, okay, gotcha.
Yeah, you should send them an email and demand like a refund. Because I sent you a link to what choline looks like. Like it's attached, like it's actually bound to the 3 methyl groups, but in the image that they use, it's not bound. They forgot to draw a bond there.
Oh, okay.
That's stupid.
Screw them. That affected mine.
Yeah.
Score. Okay.
They literally messed up there. Yeah. Whatever.
Yeah, that's fine. All right.
Yeah.
I was in the right context.
Would have been right though, if they didn't mess up.
Okay, so
That's stupid.
All right, I'm gonna give myself a 125 on this stuff. Now it's one question, but this question we can go through this one and finish up. This one was hard, and I know what this pathway is. Like I know about what this is. I had a really hard time with this question because it was hard. Like, I was just like overwhelmed with the amount of crap on here, and
okay, let's see. So, metabolic role of metabolite B. Okay. In fatty acid beta oxidation, which condition would not lead to excess carnitine? Okay, so let's see. It seems like CPT1 takes carnitine and makes it into something else. CPT2 makes carnitine. So we want it to not make carnitine, right?
Yeah, so you don't want excess carnitine. And again, I was trying to use like content knowledge to get to this, and
no need for content. Just look exactly at what's in front of you. I see CPT1 takes carnitine and turns it into something else, making it less carnitine left, right? And CPT2 does the opposite. It makes more carnitine, right?
So, okay. So, I was overthinking this. Mm-hmm. So basically, that was not a hard question.
Yeah. So basically, they're saying what would not lead to excess carnitine meaning what would lead to less carnitine.
So it would not lead to less. Okay.
That would lead to less. And since
so CPT1 would lead to excess carnitine and...
Wait. CPT1 takes carnitine and uses it up, though.
Oh.
You see that up top?
Yeah.
Like, show me using your cursor.
Yeah, here.
Yeah, so CPT1, right? So let's say CPT1, you said enzyme deficiency. Let's say CPT1 broke, right?
Okay.
That means that it's not going to take the carnitine and turn it into that other thing. That means that you're going to have excess carnitine, right?
Oh, so that's a negative feedback or whatever.
Yeah. Now, CPT2 takes that other thing and makes carnitine, right? So CPT2 would result in excess carnitine, but if CPT2 breaks, like you have a deficiency of it, you will not have that excess carnitine.
Okay. Yeah, I think I just got a little bit like overwhelmed and like I knew what this stuff was and I was worried they were gonna like I had to know the content to get to it, like with the shuttle and all that stuff.
Mm-hmm. Yeah.
All right.
I would just look at each of these and see what effect they have on carnitine. So like the carnitine carrier protein, that's the thing that changes so carnitine turns into that other thing, like the whatever R carbonyl group carnitine thing, and that thing moves through that carrier protein. So if that broke, it just won't enter into the mitochondrial matrix, but it won't have any effect on excess carnitine.
Yeah, because we already had it for CPT1, like we already had carnitine.
Mm-hmm. Yeah.
So that's not going to make it go up if there's less. So this would make,
Yeah, and then HS-CoA, that seems to be working towards making, carnitine, it gets used up. Okay, so high levels of that would produce more carnitine.
Yeah, so this makes the carnitine, and we don't want that to happen. So if that's okay, I was overthinking that question.
Yeah, so see how so far all the questions we've gone over, we look at the question first, we try to answer it to the best of our abilities, like just by looking at the question, and then if we can't, then we look at what's relevant in the passage. But at no time did we ever really read through the passage or deal with those charts with all this crap over here, with 3 different lines and stuff like that.
Right. Okay.
So so when you do these, try to attack that question first and try to gain as much information as you can from that question without worrying too much about the content. You can have everything memorized, every beta oxidation pathway memorized and stuff, but this thing it has it right in front of you and you can just just try to
it's very defeating because I did really bad on the MCAT last year and I'm not I don't know all the content perfect, don't get me wrong, there's some things I can know better, but it's I talked with you and knew a lot of content and got a lot of stuff wrong even knowing the content.
Yeah, because it's meant to be a a critical thinking test. Because
it's just why the heck did I learn what I did in college and go through all this crap?
That's for the GPA aspect, and then the MCAT, just like in high school, the GPA aspect is what you know, right?
Yeah.
And then the SAT, ACT, MCAT, PCAT, GMAT, GRE, they're all kind of they're just meant to not be what you know, but how you can apply what you know or how you can apply what is given to you in this new context, to apply it.
Yeah, I'm trying to figure that out now. I'm also figuring out content review overall is kind of a waste of time.
Yeah,
I never liked that anyway. I always thought it was stupid. But...
Yeah, do a targeted content review.
Yeah.
When I said the amino acids STY to know them, most people would be yeah, I have them all memorized, I know them, I know how to draw them and stuff, but do they know that those are the ones that are involved in phosphorylation? I don't know if they'll like know that part, but you can basically like deduce that by knowing that they have an OH group, and from that you can deduce other questions that ask like what, like that question we had, like the amine group of the amino acid is, you know, has a reaction with what functional group of PLP, the OH one, because that acts as a nucleophile.
Yeah.
And then, you know, nucleophile because it's an oxygen and it's very electronegative. So the other question with, like, you know, the more electronegative it is, more something on the H spectra, then you're able to determine that it was COOH because it has most oxygens. Like, yeah, if you can connect all these together, you'll be able to basically figure out like any of these stuff. Because yeah, like biology, again, remember it's just applied chemistry, which is applied physics. So
yeah, having a biology background helps a little bit, but not that much, honestly.
I think it steers people in the wrong direction, because when they're looking at a question, they're trying to access like their mental Rolodex of like, oh yeah, I remember when I remembered this, when I learned this in class, but try to stay like as focused on just exactly what they're asking, and try to like figure things out just from what they have in front of you. Try that with like you know, we did that with the tables too. Like not even looking at the question, just in the table, what kind of patterns can we see?
Okay.
All right.
All right, cool. When's the next time you think we can work together? Like, I know 4th of July Sunday.
Yeah, like like
I'm free. I'm free. I'm actually off work Monday too. So whatever you want to do.
Yeah.
Or if you're available, just like let me know, I guess, by email.
Yeah.
And
yeah.
Yeah, I mean, we can work together maybe longer, but
yeah.
Also,
so,
I've used pretty much. You go ahead. Sorry.
So for the other questions that you have here, if you can, like, you know, take screenshots of them.
Yeah, I will.
And send them to me. Like, I guess, like, you know, you're gonna go over this test because you haven't gone over it yet.
Yeah, I'll go through it because I just took it yesterday.
Yeah. So then, you know, the questions that still don't make sense after you go through it, you can send them to me, and then, then we can meet and we can go over those.
Okay.
And
cool.
we'll have like yeah.
And I know we haven't gotten to like cards yet. Like, I know I'm good psych-soc. I know I get like 129 higher than that. Like, I'm good to go there. The only thing I miss is like sometimes tables and things occasionally, reasoning, which we're working on now anyway. Cars, I did most all the AMC stuff already. I also did all of U-World cars, so I'm like, what should I do now for that? I'm generally like, I might miss 1 or 2 questions per cars passage. It depends. Some passages I just suck with and just get like everything wrong.
Yeah. We can go over.
I don't have to do that. Run out of stuff.
Yeah, we can go over those passages together then.
Okay, cool. I'll get a few. I'll look for a few. Maybe we can do like one. Look through a few that I've done bad on, and then maybe we can go through one. You can see like what my approach is.
Exactly. Yeah, we can
cool.
do like maybe like 2 of them like each time we meet, or like 1.
That sounds good. Yeah, for sure. All right, cool. How much do I owe you tonight?
Just 100.
Okay, cool. All right. Thanks, man. Helpful, Shane.
All right, no problem, man.
Okay.
Good luck. All right.
All right.
See ya.
Bye.